Hello, I'm Kirk Weiler, and this is Common Core Algebra 2. Today, we're going to be doing Unit number 5, Lesson number 1 on sequences. So sequences were a topic that you saw repeatedly in Common Core Algebra 1, but were completely and utterly absent in Common Core Geometry, unless your teacher decided to sneak them in some way. So today, what we're going to be doing is reviewing a lot of the basics about sequences. So if this seems like primarily a review lesson from a couple years ago, you're absolutely right. Let's jump right into the technical definition of a sequence. So what is one exactly? What is a sequence? Well, a sequence is a function, we all know what functions are, that has as its domain the set of positive integers, i.e. 1, 2, 3, 4, etc. That means that the only thing that can go in as an input is a whole number, a whole positive number, 1, 2, 3, 4, etc. So really, technically speaking, a sequence is really just a list, 5, 7, 3, 12, 14, -6, right? Where this corresponds to f of 1, this is f of 2, this is f of 3, etc. All right, so a sequence is a function, but its inputs really just tell us which number in the list that we're taking. Are we taking the first number of the list, the second number, the third number, the fourth number? All right, that's all that is. So let's continue to look at sequences. All right, let's take a look at a sequence defined by the equation a of n equals 2 times n minus 1. Very often the input variable for sequences is called n instead of x, and n really stands for like integer, an integer number. So letter A just says, find the first three terms of this sequence denoted by a sub 1, a sub 2, and a sub 3. So this is really simple. A sub 1, or the first element in the sequence, is just a of 1. These two things are the same. All right, but the rule just says, we're just going to take the input, multiply it by 2, subtract 1. We'll have 2 minus 1 gives me 1. So my first element is 1. My second element, a of 2, is 2 times 2 minus 1, or 4 minus 1, which gives me 3. A3, my third element, is my function evaluated with an input of 3. And that's equal to 5. Right? So that's it. And you can already tell what's going on here. We're generating the odd integers, right? So what this sequence is a sequence of the odd integers. Okay. Letter B. Which term has a value of 53? Now, what we don't want to do is figure out a of 53. We don't want to do that. In fact, let me put it in red. All right. I want to know which one of the terms, so somewhere out here, right, somewhere out here, there's a 53. And I want to know what n is equal to. All right, well, that's easy enough. I'm just going to take 2n minus 1, set it equal to 53, get 2n equals 54, and n equals 27. So the 27th term, or the 27th number in this list, is 53. Letter C, explain why there will not be a term that has a value of 70. Well, one way of just explaining this is all the terms appear to be odd. Another way of doing it, though, is doing exactly what we just did. Right? We say, well, let me figure out the value of n. So I'm going to get 2n equals 71, divide both sides by 2, and I'm going to get n equals 35.5. But this is impossible. Okay, and it's impossible because n must come from this set. It's got to be 1, 2, 3, 4, 5, etc. Because n just stands for, our place in line, if you will. Our place in line. Are we first, second, third, fourth, fifth, etc.? You can't be at the 35.5 place in line. You just can't be. You can be at the 35th place. You can be at the 36th place. You can't be at 35.5. All right. So pause the video and write down anything you need to. Okay, clearing this out. Let's get a little more work with sequences. Exercise 2. A sequence is defined using the recursive formula. All right, so this is a term probably buried somewhere deep in your head. Recursive formula. F of n equals f of n minus 1 plus 5, with f of 1 equals negative 2. So let me just write this down. All right. Now this is function notation. All right, we know f of 1 is equal to negative 2. This is our first term. Let's see what f of 2 is equal to. Well, if we let n equal 2, and we just plug it into this formula, we'd get f of 2 equals f of 2 minus 1 plus 5. So f of 2 is going to be f of 1 plus 5. But f of 1 is negative 2. So negative 2 plus 5 is 3. In fact, the way that we should interpret this formula is we should just say each term is 5 more than the previous term. That's how we interpret that. But that makes the rest of these things quite easy. F of 3 is going to be f of 2 plus 5. And that's 3 plus 5, and that's 8. So here's our first term, here's our second term, here's our third term. Our fourth term, f of 4, will be f of 3 plus 5, and that'll be 13, right? And finally, f of 5 is equal to f of 4 plus 5, 13 plus 5 gives me 18. So there they are. Now, this isn't a particularly important sequence. What is important is being able to interpret that rule. Now, letter B asks us to figure out the value of f of 20. All right? Now, one way to do this is to just keep going. Let me figure out f of 6, f of 7, f of 8, f of 9. But there must be an easier way to do it. So I want you to think about this a little bit, and I've even given a hint. Think about how many times you have to add 5 to negative 2. Think about that a little bit. All right, this is particularly tricky because remember, here are our terms. We have negative 2, that's our first term. Then we have 3, that's our second term. Then we have 8, that's our third term. And then 13, etc., right? Well, to get to our second term, we add 5 once. To get to our third term, we add 5 twice. To get to our fourth term, we add 5 3 times. And to get to our 20th term, we're going to add 5 19 times. See, it's tricky because you'd think, oh, well, I should add 5 20 times. But no, you only add it 19 times because you start at the first term, and when you do that, you get the 20th term is 93. There we go. It's kind of cool. So, pause the video, write down anything you need to, and then let's keep going. All right, let me clear out the text. All right, exercise 3. Determine a recursive definition. Okay, that means a definition where one term is based on the previous term or terms for the sequence below. Be sure to include, it's very important, be sure to include a starting value. All right, well, think about this a little bit. What's the pattern? How are we going from one term to the next? Sometimes that can be difficult, sometimes it can be easy. What are we doing? Well, it looks like each term is 2 times the previous term. So there's our definition. F of n equals 2 times f of n minus 1. Each term is 2 times the previous term. Now the problem with this is it's not enough. We also have to say that f of 1 is 5, because this certainly tells us how to get from one rung to the next rung on our ladder, but this tells us what rung we start on, right? All right, so these two put together are our recursive definition. Recursive definition. All right, pause the video now. We'll clear it out. We'll try a multiple choice question. Okay, let's do it. Exercise 4. For the recursively defined sequence, blah, what is the value, or the value of t of 4 is what? So pause the video now and play around with this, okay? All right. Well, in a situation like this, where we have a sequence defined recursively, all right, and we have a starting value, and then we're asked for a term that's pretty low. We want the 4th term, right? Then we're just going to do it the old-fashioned way. We're just going to kind of crank through, get the 2nd term, the 3rd term, the 4th term. So let's take a look at what T2 is. T2 is T1 squared plus 2. So that's going to be 2 squared plus 2. That's going to be 4 plus 2, and that's going to be 6. T3 is going to be T2 squared plus 2, and that's going to be 6 squared plus 2, and that's going to be 36 plus 2, and that's going to be 38. T4 is going to be T3 squared plus 2, which is 38 squared plus 2. This is where you might want a calculator, and that is going to be 1,446. And there it is. So, recursively defined sequences, which not only come up in Common Core Algebra 1 and Common Core Algebra 2, but also on the SAT exam, at least the subject exam, are important. And the most important thing is to really just be able to articulate the rule. This rule says every term will be found by taking the previous term, squaring it, and then adding 2. And once you have that pattern, it's pretty easy then to clock through the different terms in the sequence. Of course, this would be amazingly inefficient if we were looking for t of 100, unless we had something like a spreadsheet. Spreadsheets can calculate recursive definitions for sequences very quickly. Anyhow, pause the video now and write down anything you have to. All right, let's move on. Exercise 5. One of the most well-known sequences is the Fibonacci, which is defined recursively using two previous terms. Its definition is given below. Here's the definition, and here are the two starting terms. It says generate the values for f of 3, f of 4, f of 5, and f of 6. In other words, the next 4 terms of the sequence. Now, I'd like you to pause the video now and see if you can interpret what that recursive rule is saying. All right. Well, here's what the recursive rule is saying. To calculate any term, we're going to take the previous term and add it to the one before that. So in other words, f of 3 is simply going to be f of 2 plus f of 1. Those are both 1. So we get f of 3 is 2. F of 4 is equal to f of 3 plus f of 2. But we just calculated f of 3, it was 2, and we have f of 2, it's 1, so f of 4 is 3. F of 5 is f of 4 plus f of 3, And that's going to be 3 plus 2, and that gives us 5. And finally, f of 6 is going to be f of 5 plus f of 4, which will be 5 plus 3 gives us 8. The famous Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21, etc. All right, gotten by producing each term by adding the previous two terms together. All right, you're going to play around with that a little bit on the homework when you subtract terms instead of adding them. But for now, pause the video and write down anything you need to. Okay, let's clear out that text. Now, taking a recursive rule or an algebraic formula and translating it into a sequence is pretty easy. Going the other way around, taking a sequence and bringing it back, that's pretty tough. Okay, especially because you have to remember that the first number that goes in has to be 1. The next number that goes in has to be 2. Now here we're looking for an algebraic formula, so not a recursive definition, but actually an algebraic formula. Now somehow we got to have 1 go to 4, so 1's got to somehow go to 4, 2's got to go to 5, 3's got to go to 6, 4's got to go to 7, etc. Well, it looks like what I have to do is take my input and add 3. So that's pretty easy. A sub a of n equals n plus 3. I think that's simple enough. Letter B, what's the pattern there? Pause the video and think about that pattern a little bit. 2, 4, 8, 16. Now remember, when 1 goes in, the formula's got to stick out 2. When 2 goes in, we have to get 4. When 3 goes in, we have to get 8. When 4 goes in, we have to get 16. But that's 2 to the first. That's 2 to the second. That's 2 to the third. That's 2 to the fourth. So it looks like a of n is 2 to the n. All right? Yeah, I got that. I got this, right? All right. I bet the next one's pretty easy too. Pause the video and see if you can come up with a formula for that. All right. Well, when n is 1, our formula has to spit out 5. When n is 2, our formula has to spit out 5 divided by 2. When n is 3, our formula needs to spit out 5 divided by 3, etc. So I'm thinking my formula is a of n equals 5 divided by n. Make sure that looks kind of like an n. Yeah, I think that's it. Oh boy, now we're going to get a little bit harder. All right, -1, 1, -1, 1, etc. So somehow I need a formula that just flip-flops between -1 and 1. All right, there's a lot of possibilities here. So what I want you to do is pause and think if you can come up with a formula that will give you that. All right. Well, again, there's many that would work, but here's the classic. Right? A of n equals -1 to the n. Because if I put 1 in there, I'll get -1 to the first, which will be -1. If I put 2 in there, I'll get -1 squared, but that's +1. If I put 3 in there, that'll give me -1 cubed, but that'll be -1, etc. All right, now letter E is particularly tricky, okay? Because somehow, when we put n equals 1 in there, we're going to get 10. When we put n equals 2 in there, we have to get 15. N equals 3, we have to get 20. Now, a lot of people want to say the following. A of n equals 10 plus 5 times n, right? Because you got your starting value, and then clearly these are going up by 5 each time. But the problem is then a of 1 would be 15, and a of 2 would be 20. So we're off a little bit there. We're 1 too high. So in fact, we can't have 10 plus 5n. We have to have 5 plus 5n, right? And then it will give us the results we want. I think the last one's probably not all that hard. I think a lot of people will see what the deal is, so take a moment and try to figure that one out. All right. Well, did you get this? A of n equals 1 over n squared, right? 1 divided by 1 is 1. 1 divided by 2 squared is 1/4. 1 divided by 3 squared is 1/9, etc. We have it. All right. So this is a tough skill, though. This is probably what students find the singularly most difficult thing, understandable, because to come up with a formula is much harder than to evaluate a formula. So don't get discouraged on these. Get as many of them right as you can, and then move on. All right, pause the video and clear out the text. Or I'll clear out the text. It's hard for you to clear out the text. Okay, one final problem. Exercise 7 says, which of the following would represent the graph of the sequence a sub n equals 2n plus 1? Explain your choice. Well, I want you to think about this a little bit, all right? And then try to explain it. Okay, let's talk about it. Well, what do we know? We know that the domain is 1, 2, 3, etc. Right? And therefore the range will be, 2 times 1, 2 plus 1 is 3. 2 times 2 is 4 plus 1 is 5. 2 times 3 is 6 plus 1 is 7, etc. In other words, we have the point 1, 3, the point 2, 5, the point 3, 7, right? The next one would be 4, 9, etc. But that's this graph. Now you might say, well, wait a second, all these graphs basically look the same. That's that graph, and that graph. It's not this graph because there is no n equals 0. All right? For the same reason, it's not this graph. And it's not this graph because on this graph you'd have things like n equals 1.5, n equals 2.3, right? It's just these collection of dots. That's it. All right. Pause the video now and write down anything you need to. Great. Let's clear out the text, wrap up the lesson. So in today's lesson, we reviewed what a sequence was. A sequence is a very special type of function. Now, that's the technical way of looking at it. I look at it as an ordered list, not necessarily a list that goes up or a list that comes down, but just a list of numbers that are in a particular order. The input to a sequence's function simply tells you where you are in line. Are you the 5th position in line, the 7th position, the 1st position, right? And the output then tells you what number is in that position. We can define sequences two different ways. Either just with a formula that literally says, hey, a of n equals 5n minus 3. Or we can define them recursively by saying, look, the way I calculate any term is by taking the previous one and adding 7 to it, or taking the previous one and multiplying by 5, right? That will also generate a sequence of numbers, as long as you know what number you start with. All right. Thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.